Hello, my name is Ian McQuarrie. I'm a senior technical staff member with the IBM Corporation. Today I'd like to take you through a presentation on IBM SAN Volume Controller, Performance Monitoring and Analysis. Topics I'll be covering are as follows. First, I'll briefly describe the purpose and objectives for performance analysis. Next, I'll provide a methodology and approach to performing performance analysis. Then I'll provide several rule of thumb values that can be used for performance monitoring. And then the remainder of the presentation will be spent on examples of analysis performed to solve actual client problems encountered. Before I get started, I'll need to make a few disclaimers, which are always appropriate for any type of discussion involving performance. First, the operating limits pertaining to monitoring that are provided in this presentation do not represent the maximum operating limits of the related components, but rather are suggested limits selected with an emphasis on availability and maintaining stability in the SVC SAN environment. Next, much of this presentation is intended as a best practice, and as with any best practice, there may be specific and valid reasons why the limits and rules discussed here may not be appropriate for a given environment. And then finally, this presentation is intended to provide practical guidance for performing performance monitoring and analysis that could be put to use with a moderate amount of effort and experience. It is not an all-encompassing guide to performance monitoring and analysis. Okay, performance analysis purpose and objectives. There are two primary applications for performance analysis. The first is to facilitate proactive monitoring. Here we profile and monitor principal performance metrics. We monitor to a predetermined set of operating limits, watch for trends and shifts in workload, and take action to maintain or restore limits. The second application is for reactive problem isolation. Here we correlate reported symptoms, defined by scope, time, and duration of the impact, to metrics. And we identify influencing workloads so action can be taken to mitigate or resolve the problem. The analysis in this presentation was performed on the following 4 TPC reports: by volume, by port, by I/O group, and by managed disk group. Additionally, the analysis was performed using Microsoft Excel spreadsheets and pivot tables. Now we'll start looking at some actual data. In this by volume report for our example cluster prod SVC1, the aggregate data rate is up around 4.5 gigabytes per second. There's nothing alarming in this data. A cluster of CF8 nodes can safely do 8 gigabytes per second if workload is sufficiently balanced across resources. That 8 gigabytes per second per cluster value is the first of the rule of thumb values I'll be providing. I'll explain how I arrived at that value later in the presentation. As we saw from the previous chart, the aggregate cluster data rate is not very revealing. Breaking that workload out by individual host often provides much more insight. This can be done natively through TPC by generating individual reports for each host of interest. However, what I'm going to use and discuss in this presentation is a report that is derived from merging the standard TPC by volume report with the SVC configuration data through the use of a standalone script. The columns added to the by volume report by this script are host, I/O group, preferred node, and RC, which is the remote copy consistency group if the host participates in one. I'll tell you where you can obtain and how to use the script at the end of the presentation. Now I want to briefly demonstrate how to make use of the new columns we've added to the by volume report. I've opened the CSV file which was produced from the script that merged the by volume report with the SVC configuration file. You can see the new columns that have been added: preferred node, remote copy consistency group, I/O group, and host. If this host were part of a cluster, additional hosts would be listed in columns to the right. Now I'll show you how to use a pivot chart to create a by host view. I'll add time to the x-axis and our new host field to the series. For this demonstration, I'll plot total data rate. Now, that's hard to read, so we'll convert that to a line graph. And there's the by host graph. Now you can't see this in the recording, but if you hover the cursor over the peaks, you'll get a label that will show you what the host name is and the interval that the peak occurred in. So in this case, we're looking at host DW node 22. You can see all the hosts are listed, but we'll single out host DW node 22. So there's a total data rate chart for host DW node 22. Additionally, we can move the host over to the filter field and then break that data rate out by I/O group. So very quickly we can see that that data rate is spread across I/O groups 2 and 3. We can do the same for preferred node. And again, very quickly we've produced a chart showing the total data rate spread across preferred nodes 23, 24, 25, and 26. Now, let's look at the by host report we created. There are several hundred hosts contributing to that 4.5 gigabytes a second we saw in the by volume report. But now we can see only a small number of the hosts are contributing the bulk of that workload. On the next chart, we focus on the top 3 data rate contributors. Most clients have some idea as to which applications are generating the most significant amount of workload, but it's often insightful to see when the peaks occur and how much workload they are contributing relative to each other. Now we'll focus on host DW node 22, the blue line in the graph. The next graph shows the workload for DW node 22 broken out by I/O group. We can immediately see which I/O groups it's on and how well the workload is balanced between them. In this example, we can see a significant bias towards I/O group 2. Now in this graph we look at DW node P8. This is another one of the heavy hitters we saw from the by host report. Again, we're breaking the workload out by I/O group. In this case, all 4 I/O groups are being accessed, but again we see a strong bias towards I/O group 2. Now let's take a look at the by I/O group report. Here we're looking at the aggregate data rate across the SVC cluster broken out by I/O group. Immediately we see a strong bias towards I/O group 2. I/O group 2 is very busy at peak times with a data rate of just over 2 gigabytes per second. This tells us that the SVC ports must be extremely busy since they are running at roughly 2 times the data rate of the I/O group. This is because the SVC ports are handling both front-end host traffic as well as back-end controller traffic. Now comes the next rule of thumb. 2200 megabytes per second per I/O group should be considered the upper limit for an I/O group consisting of CF8 nodes. This rule of thumb relates back to the previous 8 gigabytes per second per cluster rule previously stated. Now that we have a concern that we may be overdriving ports, we will focus in on the by port report. But first I'll provide another rule of thumb. Ports running at or over 67% of line speed are saturated, and fiber channel flow control will likely be impacting response times. That's 538 megabytes per second for 8 gig ports. Saturated ports can have widespread implications. Typically, the impact is to hosts that are not the ones saturating the ports. Potential also exists for dropped frames that drive error recovery and response time spikes. Looking at this graph, we can see there are several ports that are reaching as high as 750 megabytes per second, and that would be a concern. Note that it's the 67% of line speed rule that the cluster and I/O group limits mentioned previously are based off of. 538 times 8 ports for an I/O group gets us to 4304 megabytes per second, but we need to divide that by 2 since the port data rate is running 2 times the front-end I/O group data rate. So front-end I/O group data rate limit is 2144 megabytes per second, and if we apply that to a 4 I/O group cluster, we get 8576 megabytes per second. Now I'll take you through a correlation example. This chart shows the 8 ports for I/O group 2, which contains the 4 ports that are being overdriven. If we're to do anything about this problem, we will need to know where this workload is coming from. Going back to the by host graph, it's easy to see that it's host DW node 22 that is pushing the I/O group and associated ports so hard. Hovering the cursor over the peaks within Excel will identify the interval which can be compared to peaks in other graphs. In this case, the peaks match the peaks in both the I/O group and port reports. So now we know where the workload is coming from. We can think of options to better balance it across resources. 2 obvious options come to mind. One is we could balance the workload better across the 2 I/O groups, or spread across additional I/O groups. Option 2 is we could lower the port utilization by zoning DW node 22 across all 4 node ports where it's currently zoned across only 2. Now I'll take you through another correlation example. In this case, the client provided host side data that singled out several VDIFs. This was done based on IOStat data, which showed that these LUNs were performing notably worse than others at the time of the reported slowdown. The chart shows the read-write response times for one of the identified LUNs. Note that this is a by preferred node view, which was derived through the use of a script. Plotting by preferred node is a quick way of identifying which node a given VDisk is running on. Node ID 26 corresponds to node 5 of I/O group 2. Note that the response time spikes for V0004 match the reported time of the impact. Now that we've identified the VDisk response time spikes that correspond to the time of the reported impact, we begin looking for influencing workloads. Looking at the aggregate back-end response time for node 5 also shows this same pattern. Hovering the cursor over the graphs within Excel shows that the peak intervals match between the VDisk graphs and this managed disk group graph. It's clear that at least one back-end controller is not performing well. Now focusing on individual managed disk groups, we can see our pattern again in 2 managed disk groups, prod5 DG1 and prod5 DG2. Both of these managed disk groups happen to reside on the same back-end controller, prod5. So our problem correlates to elevated response times on controller prod5. Since the response time graph for volume 4 matches the response time graph for controller prod5, it initially appears that volume 4 resides on controller prod5, but it turns out that volume 4 actually resides on a different controller. So if the elevated response time for volume 4 is not directly related to prod5, then what do they have in common? Again, looking at the by host data shows that the workload that is driving the elevated response times on prod5 is coming from host DW node P8. When we look at this by I/O group, we can see that the majority of the workload is going to I/O group 2. Now looking back at the by preferred node view for volume 4, we see that volume 4 is sharing I/O group 2 with host DW node P8. So what's happening here is the additional workload DW node P8 is putting on I/O group 2 is stressing the I/O group to the point where other volumes on I/O group 2 are being impacted. So now that we know what volume 4 and prod 5 have in common, we have options to resolve the problem. We could attempt to better balance DW node P8 workload across all I/O groups, or we could move the response time sensitive application to a less impacted I/O group. Here's another correlation example. In this case, the client is reporting a severe performance degradation, which is understandable given the average aggregate response time for the cluster has climbed to 180 milliseconds. Now we begin to look for the influencing workload. Looking at the write response time on the back-end disk shows that all managed disk groups are being impacted to some extent. There are multiple tiers of storage here, so what could be in common? With all of the managed disk groups being affected, something to be suspicious of are the SVC ports, since they are common to all of the back-end disk controllers. Critical metric there is buffer credit depletion. Overdriven devices, also referred to as slow draining devices, often result in buffer credit depletion on the SVC ports. Buffer credit depletion can have widespread implications on the performance of the SVC cluster. TPC presents buffer credit depletion as a count, which can be difficult to use for monitoring and comparison purposes. What we really want to know is what % of the time a port is spending with no buffer credits available. The following calculation can be added to a column in the by port spreadsheet to add buffer credit depletion percentage. The general rule for buffer credit depletion is it should not exceed 20%. Now we're able to plot zero buffer credit percentage. In this example, the primary volumes are part of a GM relationship. Looking at the ports on the secondary cluster, we see severe credit depletion on 2 ports that look to be tracking the response time graphs pretty well. These numbers are large. Anything over 20% should be looked at. Same peaks at 1029 and 1054 can be seen in the vDisk response time graphs. So the question is, which host is generating the workload that's overdriving these ports? Clearly it's this host, NYGUIN. This is obvious because a graph of its total data rate exactly matches the buffer credit depletion graph shown previously. This host is overdriving the ports with 100% reads. However, it's the writes from the primary volumes that are being impacted. In this case, this turned out to be a non-critical host running 2 gig HBAs. It didn't need to be running this workload at this time, so the solution was simply to stop it and run this batch workload at a less critical time of day. Now I'm going to show you a workload shift example. The performance problem was reported for the data warehouse. Jobs are taking 6 times longer than normal. Historical data for BW node 22 shows a repeatable profile. Approximately 20 minutes of heavy workload separated by 1 to 2 hours of idle. I/O group 2 peaks at approximately 1 to 2 gigabytes per second, and I/O group 3 peaks around 400 to 500 megabytes per second. This same pattern can be seen in all reports prior to the reported impact. Now we'll contrast that data with data that was collected on the day of the impact. There's a striking difference observed in the 2-1 data. The shift in I/O profile coincides with the reported performance problem. There's now an additional 1 gigabyte a second of workload on I/O group 3. In this case, the workload mapped to 31 volumes that contain DB2 temp space. This was not the solution, but information the database administrators were able to use to track down the change in database behavior, which they did. The database ran out of internal buffer space and had to push more to disk. Once resolved, the workload profile came back to what it was prior to 2.1. Note that this historical data made this observation possible. Without it, the database administrators would still be pointing at the disk subsystem as the problem. Next, I want to make a cautionary comment regarding managed disk group performance. Watch for response times on storage controllers that are way out of line. even though the high response times may be associated with slower performing devices, these high response times are not completely isolated from other high performance workloads. Storage devices that are returning average times in the hundreds of milliseconds will act as slow draining devices and impact the performance of the SBC ports. Now I'd like to summarize the method and approach to performance monitoring and analysis that I've just presented. First, profile host workload using by host reports. Identify and pay special attention to the top 3 or top 5 workload generators and the critical workloads. Establish a frequency of report generation that makes sense and archive them. Be in a position where you can answer the question, what did it look like last week, last month, etc. Monitor port utilization. Watch for overdriving. Watch for buffer credit depletion on either hosts or storage ports. Use the 67% rule for individual ports. Monitor I/O groups. Provision and adjust to maintain balance. Use 2 GB per second as a warning level. Monitor managed disk groups. Excessively high response times for heavily loaded, slower performing devices can have cluster-wide implications. Back-end queuing is a good indicator that storage is not keeping up. Now I'd like to share a few analysis comments and tips. Monitor trends to maintain margins. Identify shifts in workload for problem isolation. Filter on volume utilization when assessing response time. Idle volumes often show intervals with high response times. These are not indicative of the performance of the active volumes. To remove these data points so that they do not cloud the picture of the actual response times, they can be filtered out. This is important in cases where there are many volumes being accessed by a host, but only a subset of the volumes are active. Filtering on utilization greater than 2% is appropriate in most cases. When troubleshooting, attempt to focus in on individual volumes when possible. Oftentimes, with so many volumes involved, it can be hard to see the forest through the trees. Important relationships can get diluted from view when analyzing a large number of volumes. If specific volumes of interest can be identified through the host side data, that can be valuable input into the TPC analysis. For example, LUNs showing high % busy from IO stat or application logging conditions that are associated with a specific LUN or set of LUNs. Data rate is most important for batch workloads and response time for transaction workloads. Always evaluate response time relative to the transfer size. The script used in this presentation that merges the TPC by volume report with the SVC configuration file can be downloaded from the following URL. The script is executed from the Windows command line and will prompt for the input files. Please refer to the SVC command line interface guide if you need information on using the backup command to create and retrieve the SVC configuration file from your SVC cluster. Well, that concludes my presentation. I hope you found it useful. If you wish to obtain additional and more in-depth training regarding storage performance monitoring and analysis, the following class is available. Please visit our website at ibm.com for details. If you have any questions or comments regarding what I presented here, you can email me at imacq@us.ibm.com. Thanks very much.